Hi, everyone. I'm really excited to be here virtually and talk to you guys about this project. So today I'll be talking about learning algorithmic policies in situations where we have no choice but to extrapolate, but where we want to do that in a safe way. And everything here is going to be sort of really focused on a particular application to pretrial risk assessment instruments, but there's also sort of a broader scope as well. This is joint work with Kosuke Imai and Jim Greiner at Harvard and Zhichao Jiang at UMass Amherst. So I'm going to get started if I'm allowed to switch slides. There we go. Okay. So taking, I think, the sort of broader view for a second. Right now in our society, algorithms are making a lot of consequential decisions. And they're not just making consequential decisions, themselves. Really, more often than not, they're assisting human decision makers, right? So instead of a robot firing an employee, like in this cartoon, it's really more that an algorithm flags an employee, and then a human manager looks at it and decides. Although I've heard that at Amazon, there actually is not a human in the loop. But in general, there usually is a person, right, involved, and the algorithm is really just sort of helping them make their decisions. This is especially true in the criminal justice system, as I'll talk about, but also in social policy and in medicine. And I think it's really one of the key promises of machine learning and artificial intelligence, right? This kind of learning how to intervene, right? When and how to intervene. What action should you take and when? And beyond that, I think there's also a really interesting and important path here on designing systems that are meant to aid human decision makers, right? Because we're still at this point in society, which I think is maybe a good thing, where we want humans at the reins, right? So algorithms kind of help humans that are ultimately making the decisions. Now, kind of narrowing the scope a little bit, often a lot of these algorithms as they exist are based on known and deterministic rules. So in the pretrial risk assessment examples that I'll be talking about, these are really simple, sort of just giving scores for certain risk factors. And if the sum of the scores is higher than a threshold, you do something. But this could also be the case for more complicated algorithms, right? So decision trees are known and deterministic, where anyone can just follow the decision path of the tree, and you deterministically end up in one of these nodes. This is a good thing for accountability, right? Because it makes these algorithms transparent, it makes them interpretable, but it makes it more difficult for us to learn new algorithms from existing data. And as I'll talk about, this really comes down to an issue of lack of overlap. So now narrowing the scope even more, in this paper, we focus on pretrial risk assessment algorithms. So when you're arrested, or if you ever are arrested, you have to go to a judge to have a first appearance hearing, where the charges will be read against you and you plead guilty or not guilty. And then the judge has to make a decision. They have to decide whether they should release you on cash bail or not, right? So whether they should just ask for a signature or promise that you'll come back to your court date, or whether they should require you to put money down. And if they do, how much cash bail should they assign? And then beyond that, should they do things like require ankle monitoring or other forms of monitoring? And a key aspect of our justice system is that we don't want people languishing in jail for a long time before even charges are read against them. So these first appearance hearings have to happen quickly after arrest, which means that they're very short, and a judge will see many of them in one day. And in each one of these first appearance hearings, the judge has to make a decision. And to do that, they balance between two different things. On the one hand is the risk of an arrestee not appearing at their court date, right? So skipping town, or a risk of something worse happening, like them committing a new crime after leaving jail or leaving detention. Now, the judge has to weigh that against the costs of pretrial detention, because again, in our justice system, we have this presumption of innocence, right? So you don't want to be detaining people who are presumed to be innocent. So a judge has to balance between these two things. And this is where a pretrial risk assessment score, at least ostensibly, is supposed to step in. So these algorithms use arrestee features to classify the different risks of sort of bad things happening, right? Like a new crime or failing to appear to court. And then it combines these risks to give an overall recommendation to the judge. These algorithms have been pretty controversial. So this paper is actually part of this larger collaboration with the Access to Justice Lab at Harvard that's running a lot of different randomized control trials to try to evaluate these pretrial risk scores, to try to understand what they do, how they affect judge decisions, and how they affect the criminal justice system overall. And the goal of this paper here is to try to use data from this randomized control trial to develop new pretrial risk assessment algorithms. So more specifically than that, it's not just any pretrial risk assessment algorithm. What we look at here is what's called the PSA DMF system. It's developed by a nonprofit, and it's used in several different states and several different jurisdictions within states. And the first component, the public safety assessment, or the PSA, classifies 3 different types of risks. The first is a failure to appear in court. This is an FTA. The second is a new criminal activity, an NCA. And the third is a new violent criminal activity, an NVCA. And that's the one that we're going to be focusing on for most of this talk. So the way it does this is actually pretty simple, and you can fit it on one slide. So basically, it looks at 5 different, what they call risk factors or PSA factors. If any of them are present, it assigns a certain number of points, which is different for each risk factor. And then if the total number of points is 4 or more, the algorithm triggers this flag that says the arrestee is at risk of committing a new violent criminal activity. So here we kind of see this setup, right? We have a deterministic, algorithm, and it's very transparent, right? You can just sort of read it off, and anyone can compute this thing. There's no black box at all. The second component of the system is what's called the decision-making framework that combines these different risks to give an overall bail recommendation to the judge. And I'll describe this one on the next slide. So a little bit more detail on this randomized trial. So what we have here is data from basically the first wave of this trial. So we have a little bit less than 2,000 first arrests in Dane County, Wisconsin, where the basic setup for the study is this. At each case, a coin is flipped, and if it comes up heads, the judge gets access to essentially the printout of this system that gives the risk classifications and the overall recommendation, and it also lists the risk factors that led to the classification and the recommendations. If the coin comes up tails, on the other hand, the judge basically gets nothing. So they can, get their usual information, and actually they could, if they wanted to and take the time to, compute this themselves, but they don't get the printout to actually get the recommendation from the algorithm. What we focus on here are 2 different aspects of this. First is the decision that the judge makes, so whether they assign cash bail or signature bond. And the second is we record the outcome, which we focus on this new violent criminal activity. And just for a second to be clear about the scope of this, and this is actually how it works in the law too. This is a new violent criminal activity in the quote, like predisposition period, right? So between when an arrestee was arrested and the case is over, right? So either the court case goes through or the arrestee pleads guilty. So it's kind of limited in scope and in time, but that's actually how, that's what the law mandates judges consider. So looking at the decision-making framework, I think makes our problem a little bit more clear. So the decision-making framework uses a matrix, this DMF matrix, that uses 2 different scores, the failure to appear score, this FTA, and the new criminal activity score, this NCA. They're constructed in similar ways to the new violent criminal activity score from the previous slide. But here it's basically a very, very simple rule. It just says, if both of these scores are less than 4, recommend a signature bond. And if either of them is larger than 4, recommend cache fail. So here we can kind of start to see the problem. What we want to do is to be able to learn how to move this decision boundary between signature bond and cache fail. But we only ever get to observe one of these recommendations for everybody, right? Because it's a deterministic policy. And the basic idea here is going to be to try to figure out how to extrapolate away from this decision boundary so that we can learn how to change this overall algorithm. So just to sort of signpost where we're going, these deterministic policies, as we've seen, can really cause these bad identification issues because we don't have overlap, right? Deterministically, we can separate between the different cases. And what this means is that we can't identify the counterfactual, right? We don't know, and we can't know if things would have been better under a different course of action. And on top of this, the existing status quo algorithm is really an important benchmark, an important thing to kind of pin to. And that's for 2 reasons. One is that it's already implemented, right? So it's sort of simple, but it has institutional support. It's already in the systems, right? So it is there, and it is the easiest thing to do is to not change it. The second thing is a quick
question, sorry.
Yeah, sure.
So if the judge sees the recommendation of the algorithm, if they're assigned by the RCT to see the recommendation, they're not compelled to follow the recommendation, right?
No.
So when you say the counterfactual, is that the counterfactual recommendation or the counterfactual decision of the judge?
Yeah, so both, actually. It's the counterfactual decision. So it's the counterfactual recommendation, and then that changes the decision, which then changes the outcome.
Got it. Okay,
but
thanks.
For most of this talk, I'm actually going to forget about the decision part of this. I just think about counterfactual outcomes, then I'll return back to the counterfactual decision at the end. Yeah. Any other questions, actually? Okay. So yeah, the status quo is important both because it's already implemented and also from the statistics side of it, we can actually really evaluate it with the existing data that we have, right? Because we don't need to worry about any counterfactual arguments because we actually see what's going on under this existing policy. So combining these ideas, what we do is we try to extrapolate away from the data, which we need to do in this situation, but we try to do it in a safe way. So to do that, we partially identify the value of a given policy, of a given algorithm, by looking at all sort of observationally equivalent models. We find the worst case extrapolation, and then we optimize for that worst case. This, as I'll talk about, is called robust optimization because it's robust to all these different types of sort of true states of the world. And what it does is it gives us a statistical safety guarantee that we're going to improve over the status quo. Or more specifically, we're not going to change the status quo algorithm unless we have enough evidence to show both in our data and just with models in general that we're going to do better. And to just get a sense of what is going on here, we can think about the kind of basic extrapolation question is this, right? We have a line, we see it up until this dashed line, which in this case is like a decision boundary. And now we want to say, okay, how does this extrapolate? So what's one way to extrapolate this? Well, we could say it just continues to be flat, right? Well, we could also say maybe it goes up a little bit, or maybe it goes down a little bit. And what we're going to do is we're going to end up characterizing the entire set of possible extrapolations under given restrictions on the model and say, okay, now that we've done that, let's find the worst case. But that's actually only half of the problem because we don't observe nice clean lines in the world, right? We actually observe noisy data. So what we really see is this, right? And then we can, draw a line, fit, fit a line through this data and then say, okay, for this true model, how many ways can we extrapolate, right? And we can build up this set of possible extrapolations. But then if we saw different data, we might fit a different line and extrapolate differently, right? So we can do this a few times and we see that we end up with different answers. So to combine both of these sources of uncertainty, we're going to sort of get something both to the left and the right here, right? So we're going to account for the statistical uncertainty from the noise, and then the extrapolation uncertainty as well, to get bounds and on the truth. And then on top of this, we'll try to find the best policy. I'll make that all clear in a second. So to recap the kind of high level idea, we want to account for two different types of uncertainty. One is what's sometimes called epistemic uncertainty, which is this idea that there's many different ways to extrapolate, right? So many different consistent models with our observable data. The second problem is statistical uncertainty, where we also see noisy outcomes rather than just nice smooth lines. And what we're going to do is have a robust optimization approach that gives us a safety guarantee across both forms of uncertainty. And it's only going to change the status quo if both the data and the models support improvement. And as I'll talk about, this is a very conservative approach, but it is an approach. Okay, so I'm going to spend most of this talk talking about the first kind of uncertainty, this epistemic uncertainty, and thinking about how we would construct this algorithm if we had access to infinite data. What I'm calling here is the population policy. Before I do that, I'll pause here for any questions. Okay, great. So I'm just going to dive in. Now there's going to be a little bit more math and notation. So we'll say that we have covariates X that live in some covariate space. We have actions A that are part of a potential action space, this sort of script A. And we also have binary outcomes for each individual. And as I think is clear by now, we're taking a causal approach to doing this. So we're going to be talking about the potential outcome under action A. And also, to be clear here again, I'm not really talking about the decisions for now. I'll come back to that later. So here we're looking at the potential new violent criminal activity under different actions for the algorithm, right? Whether we assign cash bail or not, for instance. The key kind of mathematical object here is the conditional expectation of the potential outcome under action A, given covariates X, which we'll say is MAX. And the identification or lack thereof of this thing is going to be driving almost all of what's happening. The other key part of the setup is that we have access to a deterministic baseline policy or algorithm, which we're calling pi tilde. And what this policy does is it completely determines the actions. So our observed outcomes are just the potential outcome under the action taken by the baseline. Right? And there's no noise or no stochasticity in here at all. It's just deterministic. And occasionally I'll be talking about the partition of the covariate space that happens here. So if we think about that DMF matrix that I showed before, it split the matrix into two parts, right? The places where the algorithm recommends cash bail and the places where it recommends a signature bond, right? So that's just a partitioning of the space depending on the action. The last thing in the setup here is we have to define actually the utility of our actions and outcomes. And as I'll talk about more towards the end, this is actually kind of almost more important than any of the statistics, right? This is sort of how we encode what we want our algorithm to do. In the paper, we take a little bit more general view on this, but here we can just think about it pretty simply. We'll say that taking an action A incurs some cost, C of A. And then regardless of which action you took, if the outcome happens, there's a utility of U, right? And if the outcome doesn't happen, then it's a 0. So basically this means that the costs and the benefits are actually separated out. And that's kind of a simple way to parameterize what's going on. But defining the costs and defining the benefits is going to be really, really important to actually learning algorithms here. Okay, so with this setup, our goal is to find a policy, pi, or an algorithm that has a high value, which is the expected utility in the population. So what we do is we average over everyone in the population, and then we average over our potential policy actions, and then we look at the utility for that action. With some tower property stuff, we can pull out the dependence on X, and we end up with this conditional expectation here. So the key question now is, even in just evaluating what the value would be for a policy that we didn't observe, is that we need to identify the counterfactuals. So let's break this out into two cases. One of them is actually pretty straightforward. So here, what do we do when our baseline takes action A? How do we identify the conditional expectation of the potential outcome? Well, the baseline action is A, and it completely determines what action is taken. So we can just use the observed outcome, right? Here, the observed outcome is the right proxy for the counterfactual. But then we have a problem on the other side, right? So what if the baseline policy is not to take action A? How do we identify this conditional expectation? So it turns out that without anything else going on, we actually can't, right? And this is where the overlap problem comes in. So it's worth thinking about how this works in the policy learning literature usually. And I've thrown in a bunch of sites here, but there's even more on this. I think it's a really, really awesome literature. But simplifying things down quite a bit, the basic idea is to use something like propensity score weighting to identify this counterfactual expectation. So if we care about the conditional expectation of the potential outcome under action A, we take our observed outcome, we look if action A was taken, and we divide by the probability that action A would be taken, right? So this is just propensity score weighting. But our problem is that these are deterministic policies, right? So the probability that an action is A is either 0 or 1. And usually this policy learning happens in situations where it's not either 0 or 1, right? So one kind of short way to say what our problem is that we can't divide by 0, right? We can't take y over 0 because that's infinity. So we have to find some other way to do this. What we decide to do is to say, okay, we have no chance of actually identifying the counterfactual, but we can at least partially identify it and divide the problem into parts where we're fine and parts where we have to actually start to worry. So we do this by decomposing the value of a policy into two components. The first is the component where our candidate policy, pi, and the baseline policy, pi tilde, agree, right? So this is where in this DMF matrix, for example, we'd be assigning a signature bond and a cache fail at the same time that the baseline PSA algorithm is. This part is fine. Here we can use the observed outcomes, right? Because that is exactly the same thing as the counterfactual. But the difficult part is the part of the value where they disagree, right? Where we want to start changing what action we're taking relative to the baseline algorithm. And this part is unidentifiable. But what we do is we say, okay, we can't identify it, but maybe we can partially identify it and then find the best policy in the worst case. So what we do is we look at all possible models for this conditional expectation. We find the worst case one, and then we maximize that worst case. A different way of writing this, because we can identify the value for the baseline policy, is as a minimax criteria. So what we're going to do is we're going to look at the maximum regret. So this is the difference in values, the maximum regret between our candidate policy pi and the baseline. We're going to maximize that. And then we're going to minimize that maximum, right? So what this means is say, find the worst case extrapolation that is the worst case for our particular policy, candidate policy. And now let's try to find the thing that minimizes that worst case. This, as I'll show or talk about, gives us a safe policy, right? Because by optimizing for the worst case, then that means in all cases, we're defending ourselves against extrapolation error. And this kind of principle of doing things this way is a special case of what's called robust optimization, where you try to solve an optimization problem where you don't know the objective exactly, or you don't know the constraints exactly. In our case, we don't really know the objective. We're also not the first people to use partial identification and robust optimization in this way. There are two great papers here. One looking at policy learning with unobserved confounding, and the other looking at IV. And in those situations, you have partial identification as well, but in a slightly different way than we do, because we don't have overlap. Okay, so looking at this way of doing things, right? Optimizing for the worst case, you might think, well, you don't have to do that, right? We don't have to, right? There are other less conservative, less pessimistic ways to do this. One thing we could do is optimize for the best case, right? Say, okay, which of these extrapolations leads to the best possible outcome under this policy? And then let's find the policy that leads to the best possible outcome. And that's like an optimistic approach, right? Or you might think about a realistic approach where you average over all potential models, right? In sort of like a Bayesian type way. We don't go down any of those roads here because of this thing about the status quo being kind of the important benchmark, right? So taking a conservative approach like this means that we're not going to change the status quo algorithm unless we're really sure that it's going to, that we can do better than it. And as I've been saying, the reason to do this is because the status quo already exists. It's not necessarily the best thing, right? And that's actually why we're trying to learn a new algorithm, but at least it exists. And at least we can be sure that we're not going to mess anything up and make things worse using our fancy statistics. So that's why we take a conservative approach here. In pictures, kind of what's going on is that we're going to say, okay, this model for the conditional expectation, we're going to say lives in a box, right? We're going to constrain what it could possibly be. And then we're going to look at this box and say, what part of this is actually consistent with the observable data? So that might shave off a bunch of pieces of this. It doesn't point identify it, right? Because there could be many models that are consistent with this, with the observable data, but it does shave it down, it makes it smaller. And then inside of this set, we're going to try to find the worst case model. And that's the thing we're optimizing for. In math, you can actually just write this out as sort of like a zeroing condition. So the first thing we're going to do is we're going to put a restriction on the class of possible models. And we kind of need to do this in order to make any progress. And then the second thing we're going to do is we're going to compute the set of all functions in that space of possible models that agree with the observable data with a little formula that is a little bit more complicated looking than it actually is. All it says is that whenever the baseline policy is to do action A, we're going to pin down our model to be the same as the conditional expectation of the observed outcomes, right? So what this does is in different parts of this space, we pin down different parts of this model, and then the rest of it, we start extrapolating away. In the paper, we show that in relatively general kind of representative cases, you can solve this two-step thing and just end up with upper and lower bounds on your functions. And I think that's kind of the mental model that we should be going with here. So basically, once we do this, we can say that, well, the conditional expectation is at most this and at least this. So we have upper and lower bounds, BL and BU. When we do this, then that whole inner optimization problem becomes really easy to solve. And essentially what we're doing is just imputing the missing counterfactual using the worst case bound. So if the baseline action is to take, if the baseline policy is to take action A, we use the observed outcomes, right? Because this is sort of already the fact that the observed outcomes are the potential outcomes in that case. And if it's not to take action A, then we use the lower bound or the upper bound, depending on whether the outcome is a good thing or a bad thing, but we just use these bounds directly, right? So this is a different way of doing imputation. So if we had not taken this kind of robust approach and just extrapolated with one model, we would be imputing with that extrapolated model. In this case, this robust approach just basically does the same thing, but it uses the worst ones. Sorry, my grandma decided to call me. I will have to call her back. Okay, right, so we're imputing with the worst case model. I think a picture hopefully will help here. And then I'll stop for questions after I explain this picture. So this is a kind of cartoon that shows what's going on. So this is an example where we have one covariate that's discrete that goes from 0 to 19. And we have a baseline algorithm that says, if that covariate is 10 or above, take action 1. If it's 9 or below, take action 0. And then in the sort of true state of the world, we have two different conditional expectations. One is the expectation under action 0, which is in red. And the second is the expectation under action 1, which is in blue. Now, everything to the right of the dashed line, we don't see the red dots, right? Because we can't ever observe what happens under action 0, because deterministically we're taking action 1. And the flip is that we don't observe the blue dots to the left. But just looking at this for a second, think, what would be the best course of action here? What's the best policy? Well, it's always better to take action 1, right? The expectation under action 1 is higher than the expectation under action 0 at every covariate value. So we should always be doing that. But unfortunately, right, we don't see this. All we see is this, right? So we need to start extrapolating to get at this. So starting from here, then we can say, okay, well, how much can the conditional expectation really change? So if we place restrictions on that and say, well, it can't change more than a certain amount, then we can start to create this sort of cone of uncertainty as we extrapolate away. So starting with action 0, if we go from 9 to 10, we say, okay, well, it can't move up too much in either direction. So we have a sort of tight bound on that. But then from 10 to 11, it can go up more and more, 11 to 12, and so on. So we get this larger cone, which means that all the way out at the value of 19, we basically don't know much of what's going on. We can also do this for the other action, right? For action 1. So that's the first step of this process, right? We're saying, let's write out all potential models and all ways to extrapolate. Now, the second step of this process is to find the actual policy. So we're going to optimize for the worst case. What this means in this picture is that we should look at every covariate value and ask, in the worst case, what's the better option to take? So starting to the left of 10, so like at 19, for instance, all the way on the right, we can see that in the worst case scenario, and actually in all scenarios, it's better to take action 1. And we keep following, we see that this is true everywhere that we already were doing action 1, right? Now we start to get into the other territory where we were taking action 0, and we can see that at covariate value 9, right, it's still better in the worst case to take action 1. This is true at 8 and 7 and 6 and 5 and 4, and then only at 3 does it start to not be true anymore. And here there's ambiguity, right? The sort of uncertainty from extrapolation starts to include the points that we actually can identify. And then the conservative approach says, okay, in that case, you know, in the worst case, we could be really making things worse by taking action 1. So let's stick with action 0. So that gives us this policy when we solve this optimization problem. Anything 4 and above, let's assign action 1, because there we can be sure that it's better to take action 1, even in the worst case. Everything below, we don't know. And so in the worst case, we could be messing things up. So let's just stick with action 0. It's important to note here, right, that this is not the best possible thing we could have done, right? If we knew, and could identify all of the points, we would say, oh, always take action 1. It's always better to take action 1. Come on, please always take action 1. But instead, we have to do this extrapolation stuff. We don't really know what's going on. So the conservative approach is to sort of push this decision boundary back as far as we can, as far as we know that action 1 is better. And then beyond that, we say, look, we don't know, we have to take action 0. So in a nutshell, that's what all this is doing. I'll stop here for any questions. Okay.
I have a
Great.
question.
Oh, yeah, go ahead.
Yeah. Sorry, I think this plot actually reminds me of something called covariance shift in certain literature about distribution shift and domain shift. So I know you're looking at a deterministic kind of case, which is slightly different with like in most OPE, like positive evaluation, like people look at covariance shift and also stochastic policies. But is there any like connection with that literature?
Yeah, that's a good question. I don't know it well enough because I know that a lot of the covariate shift stuff is essentially doing some version of IPW, right? Mm-hmm. Where there's overlap in the covariates. I don't know enough about the literature on doing it without any overlap whatsoever. I
see.
I think there's usually some kind of assumption that in a lower dimensional, like latent space, there's overlap.
Yeah.
Which in our case would be good, right? And actually, I will get to similar ideas in a second, but here there's only one covariate. Later, where we have a lot of covariates, we can make other types of assumptions, like additivity assumptions, which say that the interaction terms don't matter. And what that allows us to do is to basically look at extrapolation and overlap covariate by covariate. So there, we can actually start to get over these overlap issues. So I think it's a similar way, but without anything latent going on.
I see. Yeah, because I think covariance usually you depend on some density ratio, and then that depends on yes.
Yeah, exactly. So the density ratio in our case is still 0 or infinity.
Right.
But that's something we had not considered, was a latent variable type model and how that would show up here. But we could use it, right? So one of the things about this is we kind of took maybe the low-hanging fruit type of models that give us these upper and lower bounds, but there's more complicated things that you could plug in here, right? More complicated restrictions on the models that would give you different types of basically algorithms that pop out, but are still kind of in this framework.
Got it. Yeah, thanks.
Yeah, I think that's a great question. Any other questions? Okay. So let me just formalize one part of this. And this is the comparison between these policies. So there are two, I think, important policies to compare to here. One, as I've been saying, I think maybe too much, is we want to compare to the baseline policy, right? But the other policy that we care about is this oracle policy. This is what we call pi star, what we would do if we could actually identify everything. So in the previous example, the oracle was to always take action 1. But as you saw, that's not what we ended up with. And we actually couldn't end up with that because we're taking this conservative approach. So one thing that we want to do is to try to characterize how different we are from the oracle. So first is comparing to the baseline policy is what I've been saying. So we have what we call the safety guarantee, that the value of this policy is at least as high as the baseline. And again, this is because this directly falls out of the fact that we're optimizing for the worst case. So then what's the cost of this? We can look at the value of the oracle and the difference between that and the value of our safe policy. What we show is that it's actually bounded by the size of this partial identification model set. And in the case of upper and lower bounds, this ends up just being the expected maximum bound width. So one way of thinking about this is that safety is a conservative principle, and it could come at a cost, right? But we can actually measure and bound that cost by how tight our partial identification is. So in the previous example, if our lines were all much tighter, right, the partial identification sets were much tighter, at some point we would have also included covariate value 3 in our policy, right, and 2 and 1 and 0, right? So as we get tighter and tighter partial identification, and this might be from assumptions, then we can limit the optimality gap here. So everything that I've talked about right now has basically not included looking at data at all. So in the time I have left, I want to quickly talk about how to look at data and then actually look at data. So the basic idea to actually do this with noisy observations is to account for that noise by constructing a larger partial identification set that contains the true one with probability at least 1 minus alpha. Right, so this is essentially like constructing a confidence interval on all of these different intervals. So we call this thing m hat n of alpha. It's cumbersome notation, but it just means that there's a hat because it depends on data, there's an n because it depends on the number of samples, and there's an alpha, and this is the most important part, right? This is basically akin to the level of a confidence interval, right? What kind of guarantee do we want that we are containing the truth in this set? We show in the paper that we can actually construct this thing by using simultaneous confidence bands for the conditional expectation. This then gives us pointwise bounds as we had before, and as before, we can impute the counterfactuals by using the worst case bound. And then the way we actually solve this thing is by solving an empirical welfare maximization problem, which I could talk about later. It turns out this is a non-convex problem. It's difficult to solve. But Garobi has an academic license and they're good at solving all sorts of non-convex problems. Okay, so in the time I have left, I will just say that we can have analogous qualities as when we use data than when we had the population safe policy. So we have the same kind of bound on the safety, on the value compared to the baseline, but now it's a statistical safety guarantee. So it holds with probability at least 1 minus alpha, and it's approximate because it depends on how complex of an algorithm we're trying to learn. So the more complex the algorithm, the less we can be sure that we're actually improving over the baseline, and but also the higher or lower our statistical guarantee on including the truth will also affect our safety guarantee. The second part of this is we can also control the optimality gap, again, by the size of this empirical partial identification set, as well as the complexity. But basically, the takeaway here is that there's a trade-off between safety, so sort of having large confidence intervals, and optimality, right? Because if you have large confidence intervals, you can't really learn anything. So now let me actually talk about some of the actual data in the time that's left. And to do that, there are just 2 more wrinkles to throw, which I promised I would get to eventually. One is, if you'll recall, we have a randomized trial here where randomly some judges receive what we call a null policy, right? Which is no access to the algorithm whatsoever. And this is actually a thing that happens all the time with this sort of stuff, where a deterministic algorithm is evaluated relative to some sort of standard of care, some sort of status quo that just isn't an algorithm at all, right? And then there's a simple, straightforward, I think, policy evaluation problem. And what we found out is we can actually use that and combine that with everything I've been talking about to learn a new policy from this sort of simple evaluation of one deterministic policy. And essentially what happens is that you can subtract out everything under the null policy, and it allows us to, in the end, work with treatment effects. So the effect of taking algorithmically taking action A relative to not having an algorithm at all. This is good because treatment effects are often considered to be simpler than baseline outcomes, so we can make more stringent assumptions, and that allows us to have tighter partial identification, which reduces this optimality gap. The other aspect of this is that we need to incorporate the judge's decisions. It turns out that everything that I just said, we can just do it twice, right? Once for the potential outcome under the algorithmic action, and the other for the potential decision under the algorithmic action. So what this means is that the value contains two different components, one for the outcomes, one for the decisions, and we have to find the worst case decision and the worst case outcome now to understand the costs and benefits of our algorithms. Okay, finally, let me actually talk about doing this. So I'll first talk about learning a new NVCA flag. And specifically what we're going to do is we're going to take all of the same risk factors, everything exactly the same threshold. We're just going to change the amount of points that we assign to the different risk factors. Now, when we do this, the key thing, and I was talking about this before, is how we decide what the costs and benefits are of flagging a defendant as being at risk of an NVCA and an actual new violent criminal activity happening. So the actual monetary cost of triggering the flag is essentially zero. But there are actually real costs to this, to the extent that classifying an arrestee as being at risk of a new violent criminal activity is a proxy for like detention. So one, it puts fiscal costs on the actual jurisdiction because now they actually have to detain someone and feed them. But it also, maybe more importantly, puts really high socioeconomic costs on both the individual and their community, right? Because you're taking someone away from their family, you're taking them out of their job, out of their community. And again, because we have this presumption of innocence that I think we're all familiar with, the goal should actually be to limit pretrial detention. And actually, in the law, it says that it should be the exception. So we don't think that we can figure out everything in society right now. So the way that we get at this is by saying that fiscal and societal costs should be one, or we pin fiscal and societal costs to be one, and then we consider what happens as we increase the cost of an MVCA. And we start at one and then we grow, right? So to be many multiples of the fiscal and societal costs. I'll skip for now this part, but in the end, we end up using an additive treatment effect model for the extrapolation. And what this does is it actually means that we don't end up needing to extrapolate very much, because for every risk factor, we observe an arrestee both where the flag was triggered and where it wasn't. So to get a sense of how learning these new algorithms changes things, I'll show you the percent of recommendations that are changed. And all these recommendations that change go from triggering the flag to not triggering the flag. On the x-axis, we'll look at what happens as the cost of a new violent criminal activity increases from 1, so it's the same as the fiscal costs and societal costs of detention, up to 10 times that cost. And on the y-axis, I'll show you what happens as we ask for more statistical safety. So we increase that confidence level. So first, if we say that the costs of a new violent criminal activity are the same as detention, then either you always detain or you never detain. And in our algorithm, it ends up saying never detain. So we change everything. But as we start to increase the costs of an MVCA, we see that the algorithm reduces more and more back to the original PSA recommendation. And this also holds as we ask for more a higher level of statistical confidence, right? So either way, we're saying that both the costs of a new violent criminal activity are higher, and we also want more statistical certainty to account for the noise. So what this means is that more and more, as we sort of move to the top right of this plot, we end up just collapsing more and more back to the status quo, because at some point there's so much uncertainty relative to the actual like high costs of an NVCA, that we end up back at the status quo. Yeah, okay, so what I'll conclude with is actually just showing how the numbers change. So one of the benefits of this really transparent policy is that we can just look at how these points change for the different risk factors. So here I've reconstructed the table from all the way in the beginning of the talk, where I have all the different risk factors that enter into the NVCA score and the points assigned to them. So as we start with a low cost of a new violent criminal activity and increase it, what we're the algorithms that we learn in the end say to put less weight on the number of prior violent convictions and whether or not this is a current violent offense or not. It puts the same amount of weight on whether there's currently a pending charge and whether there are any prior felony or misdemeanor convictions. And it's really just changing what's going on with the violent convictions and whether or not this is a current violent offense. So this is the benefit of the sort of transparency of this, is we can just see what's different. So basically what we're learning when we do this and we account for everything appropriately is that we should be placing less weight on these prior violent convictions and triggering the flag less. After a certain point though, the cost of an NVCA is high enough that, again, our algorithm just collapses back to the baseline and it says, look, there's too much uncertainty here and the costs are too high, so just stick with the baseline. We can't guarantee that we're improving. Okay, I'll skip the part about the DMF matrix and just conclude here. So to recap, these deterministic decision recommendation algorithms are really important. They show up everywhere in our lives and they generate a lot of data that we could learn from, but their deterministic nature really makes it difficult for us to learn anything because of these identification issues. So in this paper, what we do is say, okay, because we have no overlap, we have to extrapolate. Let's do it safely by partially identifying the counterfactuals, right? All possible extrapolations from our data and accounting for noise, and then optimize for the worst case. And just to reiterate, this gives us this conservative statistical safety guarantee that says that we're not doing worse than the status quo. And we're only going to change things if we know we'll improve. In these data, we find some evidence that we can improve the existing PSA, but it's kind of noisy. But luckily, we have more waves of this RCT coming that will give us more data to tell what's going on. There's lots of other interesting stuff that I could talk about, but I'll conclude here. Thanks so much. The paper's up on archive, and I would love feedback if anyone reads it and has thoughts. So yeah, thanks so much, everyone.
Great. Well, let's thank our speaker. Thank you, Eli. That was fantastic. Excellent, super crystal clear talk and very impressive work. Let's open it up for questions.
I have a question. I was sort of familiar with this because of I think originally an article in the Washington Post, like an opinion piece by I think probably people from the same research group, like Avi Feller was one of them, about the algorithmic fairness of pretrial detention algorithms, specifically across racial groups. And their conclusion, I'll put it in the chat because it's pretty interesting, but their conclusion was basically that it's hard to choose just one criterion for fairness because different criteria conflict with each other. So it seems like in this analysis, you basically just optimized, your target was a utility function as opposed to satisfying criteria of fairness. But was that an aspect of evaluating the algorithm that you would consider at all?
Yeah, absolutely. So this is actually one of the things that I should have added as a bullet point at this very end. We tried to break down this problem into different bits. So first thing was, how do we deal with this extrapolation to begin with? But there actually is some evidence that this, depending on which measures of fairness you're talking about, but that this PSA algorithm doesn't satisfy a couple of them. I think like miscalibration and things like that. So a second set of things that we're interested in is how do we actually include some satisfying some measures of fairness in here as well. But that's sort of almost like a orthogonal type of problem, right? Because we're trying to deal first with, okay, how do we do this extrapolation? But I definitely think it's very, very, very important to think about fairness. And I think one way to think about that is like a different notion of safety, right? And if taking a sort of a broader view, I think these sorts of algorithms, there was this like heyday a couple of years ago where you could fit a logistic regression and do some funky stuff with it, and then there you go. That's the algorithm, and everyone's like, "This is cool. This is AI." Where there's an article about how this is moneyballing criminal justice. And then there's been a lot more recent work, for instance, from the fairness literature saying we should think harder about this stuff. We should be a little bit more careful. And I think that one of the ways to be more careful is these notions of safety, right? Like, can we do better than status quo? Can we ensure that there's fairness? Can we ensure that bad things aren't happening inadvertently? So I think that's a great, there's a long-winded way of saying, I think that's a great question. I think that's like an important future direction that we want to go in. And I think in general is an important thing for this field.
Great. Others have questions?
I have a question. So yeah, so very nice to know this type of work. So I'm mostly in machine learning and also mostly in like OPE, like use stochastic policies. So I do not know much about deterministic, but I feel it's quite interesting to know this kind of work. So I kind of have this general question on, so like you can model this as deterministic policy, but you can also think of the data as a sample from some stochastic policy. So I kind of want to know the general consideration, like when you model this deterministic versus stochastic, what's the consideration there? This is the first question. And another broader question is also about like in terms of like this algorithm aided like decision making in very critical area, like a law in this case. What's the bottleneck? I guess fairness is definitely something. I kind of want to know in your general insights on what's the bottleneck there. We need to, like from a machine learning point of view, we can help to solve, and then we can bring things to more trustworthy AI. Yeah.
Yeah. Okay. So the first question, if I can make sure I got it right, it's that we look at this as a fixed deterministic action, but there are ways to look at it as some, you sample from something and you get a stochastic.
Right.
Yeah. So in this case, we are looking at something totally deterministic in the sense that even if we got new draws of the data, we could never get to observe something different because the actual policy itself is fixed. But I think there are two different ways to loosen that. One of them is, I didn't really mention this, but this randomized trial is actually multi-site and it's in a bunch of different jurisdictions. And each one of those jurisdictions uses a different version of, for instance, this decision-making framework matrix. And one way to think about those different versions of that matrix is, okay, well, do we average over everyone in the population, right? In which case it is kind of a random policy because we could get someone from this jurisdiction or that jurisdiction. A different way to think about it is to say that, well, we can actually still say it's deterministic and say that the jurisdiction that they're in is sort of a covariate, right? So it's a deterministic function of the risk factors plus the jurisdiction. But we can still use some of these ideas, and we're planning on doing this once the data comes in, to basically say, okay, if we assume that there's no interaction terms, then we can start to get at some of these issues. Does that kind of get at this first question?
Yeah. So there are some like randomness there. You can model. You can also model that, but also like maybe it's also like for example in human decision making, you can also think like human is there. I think in this case you have this deterministic rules. So this is pure deterministic, but there are cases, I guess, maybe stochastic. You can model that in a way that has randomness in it.
Yeah, and I'll add on that. One thing is like you could say, well, there's situations where you don't know the status quo, right? If you say everyone has their own deterministic algorithm, right? Then it's random because of, you know, you can think about like random effects and things like that. So I think that's like a really interesting way forward and a way to go with this. On the second question on the bottleneck, I don't know if this totally gets at this, but one of the things that was found in this first wave of this RCT was that judges don't really change their behavior very much. And I didn't really get to show this slide. And I guess part of the joke of the slide is that nothing is going on, but we did try to take into account the judge's decisions, as I talked about. And what we found is that we could learn nothing. And that's because there's too much noise in the judge's decisions to actually tell if you recommended cash bail, for instance, if that would actually happen. And there's too much noise even across the covariate space. So in our case, if you're conservative, that means, okay, don't change anything. So I think one of the things in designing these systems is actually designing something that people actually use, right? And actually like care about and take credibly. And I think that might be almost like an extra statistical, extra computer science type concern of like, how do you actually design these systems just so that there's trust built into it, right? So if a judge sees this recommendation, they say, oh, you know what, I actually believe this and I will actually meaningfully change my actions. But of course, if you can also make better algorithms that take into account, that's part of what we're trying to do here. You could take into account the fact that they might change their actions for, in some cases, not in others, and you could exploit that when designing the algorithm.
Got it.
So
yeah,
that's
definitely there's a lot of human AI
So-
interaction kind of trust built between human and AI. Yeah, definitely. Yeah.
I think it's a really interesting like set of questions that I'm excited to see where it goes.
Yeah, thank you for the talk. It's a very great talk. Thank you.
Thank you.
Great. Well, I have one question I wanted to ask about the, well, first, this is fantastic. Thank you for coming to speak, and it's very impressive work. I mean, and you do a lot of other things too. I should have done a better introduction for you, but I mean, your work spans multiple areas, and this reminds me a lot of a problem that I've worked on with Suchi Saria on. It's an alert system. I mean, it's really her project. My contributions are minimal, but it's an alert system for doctors in who are treating patients who are at risk for sepsis. So it's basically gives an alert to tell them your patient is at risk for sepsis. But there's a downside to doing lots of alerts. Doctors are overwhelmed with all these kinds of alerts, and so so there's a cost to it. And so there's a lot of observational study data on just what doctors do with the no alert system, and then they've implemented an alert system that there's a known function that causes the alert to occur. And then also there's been a lot of thought about designing randomized trials to evaluate an alert system and how to do that. So I think a lot of the ideas would fit well in that context. I mean, there are a lot of analogs to what you're talking about. And I remember, this is some years ago, but talking about discussions of how would you do a trial to assess an alert system, and just all the challenges, especially would you be able to do something like have it be on for a while for a particular team or doctor, and then turn it off for a while and turn it back on? I mean, I'm not sure if do you know what they did with the judges? It basically was a judge assigned to just never have this, or sometimes have it, or was it a crossover kind of thing, or?
Yeah, I mean, well, so I'll say I would love to hear more about the alert system. That's really interesting. And in this case, there's actually a question that we were thinking about with that too. For this particular site in this randomized trial, that is sort of the first wave that we got, it was by case. So the same judge would see, actually the same judge and the same arrestee, right? So say someone was released and they came back a month later, you could get it or not. So I kind of skipped over this, but we have more arrests in this data than we use because we don't know how to deal with those second arrests just yet. And partly because of this by case randomization. But I think that the randomization schemes there are really interesting, especially because one of the things that I think is kind of I guess I would call it an opportunity, is the way I see it, is that the long-term impacts, and like you were saying, you don't want to send too many alerts and things like that. The long-term impacts of these algorithms, especially as they're recommendations and they affect human behavior, you can get this weird long chain of mediation, right?
Yeah, exactly.
And so like disentangling that and figuring out, okay, what is actually even, I think even writing down what is the thing that we would optimize for, even if we knew what, you know, we could do, I think is like wide open and really interesting. And then also, you know, the actual statistics of like accounting for those chains correctly, I think is beyond that also quite interesting.
Yeah,
so
definitely. Well,
yeah.
we'll have to find a time to talk about the sepsis. I can introduce you to Suchi Saria if
Yeah,
you have interest.
yeah, absolutely.
And, that's still, I mean, a lot of big open questions there.
Yeah.
This is great. Well, I think, well, I'll open it up for any last questions. Great. Well, let's thank Eli once again. Eli, it was fantastic. We're so happy that you came, and you pulled in a great audience from all different departments. So that was excellent.
Yeah,
So
thank you for having me.
much.
Really great.
Thanks, Eli. We appreciate
Thank
it.
you.
Yeah.
Bye-bye.
Thanks, everyone.
Great. Take care. Have a great day.